Hi, I'm Professor Kelly, and this is a lecture on precedence and associativity for the Syntax and Semantics unit of CSCI 308, Programming Language Design. Learning goals for this lecture are to be able to explain precedence order and associativity, and to create precedence order and associativity rules to eliminate ambiguity in grammars with infix operators. When writing a parse tree for 3 plus 4 plus 5 using the grammar shown, we can write the parse tree as right branching and add 4 and 5 to get 9 first before adding 3 and 9 to get 12. Or we can write the parse tree as left branching. We add 3 and 4 to get 7 and 7 and 5 to get 12. And this is what's called ambiguity, when multiple possible parse trees for the same sequence of symbols. Ambiguity isn't really much of a problem for addition, but in the case of subtraction, we can get different results depending on the order in which the numbers are subtracted from each other. How can we eliminate ambiguity from grammars? In mathematics, an operator is said to have the property of being associative if the order of operations does not change the result. This is true of plus, but not the minus operator. A left associative operator, conversely, is an operator that is evaluated from left to right. We can write a rule describing a left associative operator as follows. We can replace a symbol A with A operator B or B. We create an asymmetry that forces the operator to have a left branching tree. Conversely, a right associative operator is one that must be evaluated from right to left. By creating the rule A can be replaced with B operator A or B, we force the parse tree to only branch to the right. Let's demonstrate this by writing a parse tree for 3 minus 4 minus 5. First, let's make some changes to the grammar. Currently, the grammar rules are symmetrical. Plus and minus can both branch either to the left or the right. Let's change both of them. We add a new rule. Factor can be replaced with number or variable. When we want to add or subtract, expression is replaced with expression plus factor or expression minus factor. As a result, the tree will only be able to branch to the left. We start with expression. Then, if we want to subtract, we replace expression with expression minus factor. We cannot replace factor with another minus symbol. When we replace factor, it either has to be a number or a variable. The other expression, however, can be replaced with expression minus factor, giving us another minus sign. We can replace that expression with a factor and the factors with none and get 3 minus 4 minus 5. This allows for as many minus signs as we want, but only permits the tree to branch to the left. Asymmetrical rules can force left or right branching trees. What about 3 minus 4 times 5? In this situation, even though minus is left branching, we actually want to do 4 times 5 first. We want to multiply 4 times 5 to get 20, and then we want to do 3 minus 20. Precedence order determines what operations should be computed first. This is often memorized in America using the acronym PEMDAS, parentheses, exponent, multiplication and division, addition and subtraction, also known as BEDMAS and BODMAS in other countries. We can represent precedence order using multiple rules. At the lowest precedence order, we can have expressions. Expressions allow us to add and subtract, or an expression can be replaced with a term. At the next level, we have terms. Terms can be multiplied or divided, or they can be replaced with a factor. Factors can either be replaced with a number or can be replaced with an expression, but the expression needs to have brackets around it to indicate that it is done first. If we combine this with associativity, we instead make all of these rules asymmetric. So for addition and subtraction, it's an expression and a term. For multiplication and division, it is term and factor. Factor's rule doesn't change. Let's write a parse tree for 3 minus 4 times 5. We start with expression. The expression has to be replaced with expression minus term in order to get a minus sign in. We can then replace the term with term times factor to get the multiplication symbol. At this point, we have the parse tree for the minus and the multiplication, and we just need to replace the expression, term, and factor with numbers. We replace factor with number. Term needs to first be turned into factor before it can be a number. An expression needs to be converted to a term and then a factor before it can be a number. Learning goals for this lecture were to explain precedence order and associativity, and to create precedence order and associativity rules to eliminate ambiguity in grammars with infix operators. Left associative operators can be represented by rules where the operator on the right-hand side is of a more specific type. Conversely, right associative operators can be implemented using a rule where the operator on the left-hand side is of a more specific type. Precedence order. What operators should we do first? We can appeal to PEMDAS here and implement several different rules for the different orders of precedence.